Hello class. For our last topic, we are going to be discussing commutation relations and how it relates to one of the more famous observations about the limitations of quantum chemistry, the Heisenberg uncertainty principle. So let's start with classical mechanics. A system in classical mechanics can be described nearly completely. So consider a mass falling to Earth. The following observables can be determined with a high degree of accuracy. Things like position, momentum, kinetic energy, potential energy. All of these things are known for a system, and you're only limited by your instruments. In quantum mechanics, however, there are two possible cases for multiple observables. So observables, like any of these above, can be known with a high degree of accuracy if the measurements do not change the system. However, in quantum mechanics, it is possible for the measurements themselves to actually interfere with what you're trying to measure. That brings us to case 2. Observables cannot be known with a high degree of accuracy if the measurements change the system. So how can you figure out whether or not the measurements change the system? We can do that using commutation relations with operators and wave functions. So to get there, let's first consider two variables, two observables, A and B, which correspond to operators A and B. Wave function psi of x describes the system. If psi of x is an eigenfunction of operator A, the following would be true. Operator A on psi of x would produce eigenvalue A and produce back our wave function. So lowercase a is our eigenvalue, and that is our observable. And again, an observable is something like position or momentum or kinetic energy or something like that. For another, we could have psi of x being an eigenfunction of operator b. And that would look like this. B operates on psi of x to produce eigenvalue b and give back psi of x. So this would produce eigenvalue b, which is our observable. And in this situation, we're starting with wave function psi of x, and we're getting it back at the end. So psi of x is an eigenfunction, and eigenfunctions are only possible if we produce eigenvalues. So how can both observables, A and B, be measured when the wave function is operated upon by both operators A and B? So remember, we're looking for cases in which we're trying to make two observations at the same time. We're trying to acquire two observables. And observables are eigenvalues that are produced by operators. So we need to take a look at what happens when the wave function is operated upon by both operators A and B. And we do this sequentially. So the first sequence that we could try would be operation A first and then B. And that would look like this. So operation A acts upon psi of x, and then operator B acts upon that product. So if psi of x is an eigenfunction of operator A, then after A acts upon psi of x, what we're left with is eigenvalue A and psi of x, just like what we had above here. We had operator A acting on the wave function produce our eigenvalue and our wave function. So that's what's happening here also, but then operator B is still part of the equation, and that needs to then act upon the wave function. The only case where the system is unchanged is if the wave function is also an eigenfunction of operator B. So we have just acted upon the wave function with operator A to produce eigenvalue A. Then operator B acts upon the wave function to produce eigenvalue B. And so here we have our product where we have both eigenvalues are produced. So overall, we could write it like this. Operator B acting upon the product of operator A on psi of x produces eigenvalues A and eigenvalues B and give back our eigenfunction psi of x. This is a situation where we can obtain both observables A and B simultaneously. The second case is case 2, where we would sequentially act upon the wave function first with operator B, and then act upon that product with operator A, and that would look like this. Operator A acting upon the product of operator B on the wave function, and if we were to successfully have a eigenfunction for both operators, we would produce both eigenvalues. So we would produce B and A. Now, observables A and B, our eigenvalues, are constants. So it doesn't matter what order we have them listed here. We could have AB times the eigenfunction, or we could have BA times the eigenfunction. Therefore, we can say that both of these sequences, B acting on A acting on psi of x, and A acting on B acting on psi of x, are equal to one another, because they produce the same set of eigenvalues and eigenfunction. This is to say that operators A and B successfully commute. And that brings us to developing a system where we can test whether or not the operators commute. So if we can say that B acting on A acting on psi of x is equal to A acting on B acting on psi of x, then the difference between those two, shown here, is equal to 0. And then the operators A and B successfully commute. So that brings us to equation 6.1, which is a generalized form of this, where we have operator A acting on operator B acting on any arbitrary function f of x minus operator B acting on operator A acting on arbitrary function f of x. The difference between those two is equal to 0 if they commute. However, if the difference is not 0 for any arbitrary function f of x, then the operators do not commute. As a result, the corresponding observables A and B cannot be determined simultaneously. So if we're trying to figure out if the observable A coming from operator A and the observable B coming from operator B can be determined simultaneously, we set up this equation, and if it's equal to 0, they can be determined simultaneously. If it's anything but 0, they cannot be determined at the same time. So commuting operators that successfully reach this requirement of being equal to, the difference being equal to 0, can be written in the shorthand parentheses or brackets operator A, operator B, close brackets, f of x. So now here is a table of common observables in physics and chemistry and their corresponding operators and the symbol for their operators. In the next example, we're going to show whether or not momentum and kinetic energy can be determined simultaneously for a system. So that brings us to exercise 13. Determine whether the momentum and kinetic energy of a quantum mechanical system can be known simultaneously and exactly. So here's how we do that. First, we define A for our equation 6.1 as being equal to our momentum operator. And momentum has the symbol P of x, and its operator is negative I times h bar times the partial derivative with respect to x, which I've rewritten down here. Our kinetic energy operator, E caret kinetic, has this following identity, which is equal to negative h bar squared over 2 times mass times the second partial derivative with respect to x, which we've seen before for the particle in a box. And I've rewritten the operator down here. So to test whether or not the momentum operator and the kinetic energy operator commute, and as an extension, show us whether or not kinetic energy and momentum can be simultaneously known, the difference between these two commuting expressions must be equal to 0. So here we have equation 6.1 set up. And what we're going to do is make the following substitutions: our kinetic energy operator for B and our momentum operator for A, which brings us to the following. For momentum operator, negative I times h bar times the partial derivative with respect to x times the kinetic energy operator, negative h bar squared over 2 times mass times the second partial derivative with respect to x acting on function f of x, minus the kinetic energy operator, negative h bar squared over 2 times mass times the second partial derivative with respect to x times the momentum operator, negative I h bar times the partial derivative with respect to x acting upon f of x. And the difference between these two must be equal to 0. If it is equal to 0, then momentum and kinetic energy can be known simultaneously. So over here on the left, what we're going to do is bring out all of the constants out to the front, shown here, where we have I times h bar squared over 2 times the mass, and the negative signs cancel to make this expression positive. We also have one partial derivative with respect to x acting upon the second partial derivative with respect to x acting on f of x. Over to the right, we have something similar where we have I times h bar squared over 2 times mass times the second partial derivative with respect to x times the partial derivative with respect to x of f of x. So all of these constants out front can be simplified down to I times h bar cubed over 2 times mass, and the derivative of a second derivative is just the third derivative acting upon f of x. And if we simplify the right side, it ends up being the same. And so when we take the difference between them, since they are the same, it is equal to 0. And that tells us that in a quantum mechanical system, momentum and kinetic energy can be known simultaneously and exactly for the arbitrary function f of x. So now let's determine whether or not two other observables, position and momentum, can be known for a non-arbitrary wave function, a specific wave function for a wave shown here. So that brings us to exercise 14. Determine whether the position and momentum of a quantum mechanical system can be known simultaneously and exactly at t equals 0 and phi equals 0. This is our phase angle for the following wave function. Psi of x is equal to a times e raised to the power of I times the quantity kx minus omega t plus phi. Now, at time is equal to 0 and phase angle is equal to 0, our wave function simplifies to a times e raised to the I kx. Now, a is going to be our position operator, x. And for a position operator, x, our operator is x. And when you have a variable like that that stands alone, the operation is multiply by x. For b, we have our momentum operator, p. And the momentum operator is as follows, negative I times h bar times the partial derivative with respect to x, taken from the table. And so what we're going to do to see if these operators commute, which would then give us observables that can be known simultaneously and exactly, we have to test with equation 6.1. A acting on B acting on f of x minus B acting on A acting on f of x must be equal to 0. So let's substitute in our operators and we get x for A times our momentum operator negative I times h bar times the partial derivative with respect to x times our wave function A times e raised to the I kx minus negative operator for momentum negative I times h bar times the partial derivative with respect to x times our position operator x times our wave function a times e raised to the I kx. The difference between these must be equal to 0. So step 1 is we're going to solve the left side of the equation, just a acting on b acting on f of x. So that's shown here, where we have x times negative I h bar partial derivative with respect to x times a times e raised to the I kx. So first, let's take the partial derivative with respect to x of our wave function. A is a constant, comes out before the partial derivative, and we can use the chain rule to determine that the derivative is equal to derivative with respect to u of e raised to the I times u times the partial derivative of u with respect to x of kx, where u is set equal to kx. And so when you take the derivative of e raised to the iu with respect to u, you get I times e raised to the iu. And when you take the derivative of kx with respect to x, you get k. And so when we put this all together and substitute kx for u, we get our derivative of a times e raised to the I kx to be equal to a times I times k times e raised to the I kx. Now let's plug that in for our expression of a acting on b acting on the wave function. So this will be equal to position operator x times what's left of the momentum operator, our constants negative I times h bar, times the partial derivative with respect to x of the wave function, which we just solved, to be equal to a times I times k times e raised to the I kx. Now we have a negative, an I, and we multiply all that together, we get negative I squared, and that is equal to 1. And so this whole thing simplifies to a times h bar times k times x times e raised to the I kx. And so now we're going to bank that and use it for later. And that brings us to the right side of the equation, negative I times h bar times the partial derivative with respect to x, our momentum operator, times position operator x acting on wave function a times e raised to the I kx. And so all of that is equal to negative I times h bar times the partial derivative with respect to x of x times a times e raised to the I kx. And this will be a little bit more complicated because we have a second x in our expression. And so the derivative with respect to x of x times a times e raised to the I kx is equal to, you can take a as a constant out before the derivative, and so we have the derivative with respect to x of x raised to the e I kx. Now, how do we solve that? Well, we can use a derivative identity, which is that the derivative with respect to x of x times e raised to the IAX is equal to IAX times e raised to the IAX plus e raised to the IAX. And so, when we bring that in and use it for the derivative with respect to x of x times e raised to the IKX, we get a times the quantity IKX times e raised to the IKX plus e raised to the IKX, and we distribute the a, we get a times I times k times x times e raised to the IKX plus a times e raised to the IKX. So a bit of a mouthful, but that is our full answer for our derivative of our wave function times x. And so if we make that substitution, we have negative I times h bar times the partial derivative with respect to x of x times a times e raised to the IKX is equal to negative I times h bar times that whole expression, a times I times k times x times e raised to the IKX plus a times e raised to the IKX. And again, we can distribute. Outside of the parentheses, we have negative I times h bar, which we can distribute and get negative a times I squared times h bar times k times x times e raised to the IKX minus I times a times h bar times e raised to the IKX. And out in front, we have a negative and an I squared, which is equal to 1. And so we get, finally, b acting on a acting of x is equal to a times h bar times k times x times e raised to the IKX minus I times a times h bar times e raised to the IKX. And so, when we take this solution and our solution from step 1 and put it together to test whether or not the operators commute, we get the following. A acting on b acting on f of x minus b acting on a minus acting on f of x, our function, is equal to a times h bar times kx times e raised to the IKX minus a times h bar times kx times e raised to the IKX times, or minus I times a times h bar times e raised to the IKX. And so these two cancel with one another. Negative times negative is a positive, and we are left with overall the difference between the two being equal to I times a times h bar times e raised to the IKX. And this whole quantity here is noticeably not equal to 0. What does this mean? By not equaling 0, the position and momentum operators do not commute, which means that the observables, position and momentum, cannot be known simultaneously and exactly. This famous result is called the Heisenberg uncertainty principle. And that brings us to the Heisenberg uncertainty principle, which says that for a given wave function, that in a quantum mechanical system, position and momentum cannot be known simultaneously and exactly. And now we're going to show this to be true from a different direction. So we're going to show that position is unknown using the momentum operator. So if the momentum operator is known, then the wave function psi of x being equal to a times e raised to the ikx would be an eigenfunction of the momentum operator p of x. So first we need to prove to ourselves that momentum is known. Proving to ourselves that it is known is showing that the wave function is an eigenfunction of the operator in question. So in order for psi of x to be an eigenfunction, it must produce an eigenvalue. So that's testable. We can use the momentum operator acting upon wave function psi of x and show that that's equal to negative I times h bar times the partial derivative with respect to x of wave function a times e raised to the ikx. And when we put that together, that is going to be equal to negative I times h bar times a, our constants, times the result of our derivative I times k times e raised to the ikx. Now, when we bring all of our constants together out front, negative I times I is negative I squared, which is equal to 1. And so what we're left with is h bar times k times a times e raised to the ikx. Now, a times e raised to the ikx is our wave function, psi of x. And so this is our eigenfunction. We get it back, which means that we have h bar times k is our eigenvalue. So all this means is that, yes, momentum is known. When the momentum operator p acts upon wave function a times e raised to the ikx, we get that wave function back, it's an eigenfunction, and it produces an eigenvalue. That tells us that momentum is known. So we have a wave function for which the momentum is known. Now we're going to use that same wave function and see if we can find the probability of a particle in a certain position. So we've just proven that we know the momentum of this, or that the momentum can be known for this wave function. So now we're going to use the same wave function and see if we can determine position. And we're going to determine position using a normalized wave function and find its probability, or finding the probability of a particle in a certain range. So first, let's normalize the wave function. So from negative L to positive L, our given range, we have the complex conjugate of the wave function times the wave function d of x must be equal to 1, the integral. So we can bring our constants of our wave functions out, so a star times a times the integral from negative L to positive L of the complex conjugate of the wave function being e raised to the negative ikx times the wave function itself, e raised to the ikx. The integral of that product must be equal to 1. That product itself happens to be equal to 1, since the exponents sum to 0. So we're left with a star times a times the integral negative L to positive L of 1 dx is equal to 1. And so when we take that integral, we get x, and so and we can simplify our constants out front to being just a squared. And what we're left with is a squared times x evaluated from L down to negative L must be equal to 1. And that simplifies to a squared times the expression L minus negative L is equal to 1, which is equal to a squared times 2L is equal to 1, which allows us to solve for a being equal to the square root of 1 over 2L. And so, in order to determine whether or not we can identify the position, we're going to solve for the probability of finding a particle at position x using the following expression, probability of x times d of x. So the probability of x times a little bit of x, a small range of x. So p of x d of x is equal to the probability of our wave function, which is equal to our wave function squared times d of x. And since we have a complex conjugate, we can expand that to being equal to psi of x star times psi of x times d of x. And so p of x dx is going to be equal to the product of the square root of 1 over 2L times e raised to the negative ikx, being the complex conjugate of our wave function, times the square root of 1 over 2L times our wave function itself, e raised to the ikx dx. So this is equal to 1 over 2L times d of x. So we do not know the position precisely. We say that there's a small amount of x divided by 2L. This is not a precise value. The result being that the probability is independent of position. The momentum is known, given that psi of x is an eigenfunction of the position operator p, but in this case, the position is completely unknown.